So the title of the talk is Offshore Wind Farms and the Morro Bay Project. So let me go through a quick outline here. A little bit start on climate change and to motivate the idea for offshore wind power. Then spend a lot of time talking about the technology of offshore wind power, which is really interesting, fun to talk about. Then I'll get into the specifics of the planned Morro Bay Wind Farm, bring up possible issues of concern, then a summary. A couple of things up front here. I am a proponent of this project, and I will, at the end, I'll tell you, I'm hoping this project goes forward. I understand that not everybody is going to be a proponent of this project, and I do promise to be an honest broker of bringing up issues of concern and exploring those issues of concern. I've come to the conclusion the positives outweigh the negatives. Other people may come to a different conclusion out, and that is fine. My goal today is to spell out all the issues and get you thinking about, what the issues are. Also, I need to tell you that I have no connection to this project. I don't work for any company that's building or in competition to build out this project. I have no interest in that. I'm just an observer here, and I'm very interested in climate change, of course, and the Morro Bay project can be an important tool in addressing climate change. So let's jump right in here and talk a little bit about climate change. There's an overwhelming international scientific consensus on the following 3 points. Point number one, over the past 120 years, the Earth has been warming and the climate has been changing at alarming rates. Number two, the global warming and resulting climate change of the past 120 years have been driven almost exclusively by the Earth's greenhouse effect and the accumulation of greenhouse gases in the atmosphere caused by human activities. And point three, without dramatic reduction in the emission of greenhouse gases into the atmosphere, the Earth will continue to warm and the climate will continue to change to the detriment of humankind. Stated succinctly, it's happening, humans are causing it, and it is not a good thing. Now, there isn't a reputable science organization in the world that would disagree with these 3 points. The science is clear, the science is settled, and there's no doubt about this. So what are the impacts of climate change? Well, in terms of the natural consequences of a warming world, I'll just hit the high points here. Increasing frequency and intensity of severe storms, increasing frequency of life-threatening heat waves. And by the way, heat waves kill more people than any other weather phenomenon. Increasing frequency and intensity of floods in wet regions, increasing frequency of droughts and wildfires in dry regions like our region. Decreasing mountain snowpacks and earlier snow melt, big issue here in California. Rising sea levels, increasing mortality of coral reefs, usually referred to as coral bleaching, decreasing productivity of fisheries, and loss of biodiversity. So how does this translate to the human world? Increasing economic cost, increasing competition among nations for water and food, increasing displacements of people leading to unrest, increasing threats to human health, increasing human mortality from heat waves, other severe weather events, starvation, disease, and war. Not a pretty picture. It's something we need to address, obviously. Now, there are several greenhouse gases that are causing this problem, but CO2, carbon dioxide, is the dominant greenhouse gas. CO2 drives more global warming and climate change than all of the other greenhouse gases combined. Doesn't mean the others aren't important. We don't have to worry about them. We do. But CO2 is the one of greatest concern, the one we need to address the most. So here's a plot of CO2 in the atmosphere from 1700 to 2019. It's CO2 concentration in parts per million. In the pre-industrial era, the CO2 concentration in the atmosphere was about 280 parts per million. Beginning with the Industrial Revolution, particularly ramping up in the 60s, CO2 concentrations went up very rapidly, and we're now at about 419 parts per million, which is an increase of 50% over the pre-industrial level and the highest in the past 4 million years. Now, from 1850 to 2018, the total amount of CO2 emitted by human activities amounted to about 1.6 trillion tons, not billion, trillion, 1.6 trillion tons. And about 0.9 trillion tons of that is still in the atmosphere. We're currently emitting about 40 billion tons of CO2 per year globally. So where's that CO2 coming from? Well, China's number one, accounting for about 27% of that 40 billion a year. We're number two, 14.8%. Together, China and the US account for more than 40% of CO2 emissions. Then it's India, Russia, and it goes on down from there. So let's take a look particularly at the US. And about 80% of our greenhouse gas emissions is in fact carbon dioxide. And it comes mainly from these three sectors. Jim mentioned transportation, and that's a big issue, of course. It's actually the biggest emitter within the sector within the US.
You should say a car instead of a truck.
Yeah, I think someone's muted. Maybe go ahead, or someone's not muted. Go ahead and mute, please, everyone. If you have a question, go ahead and unmute and raise the question, but hopefully there'll be enough time for Q&A after the talk here. Second is energy generation, electricity generation. That's basically electrification of the power grid. And next comes industry, mainly steel and cement production. Well, really talking today mainly about electrification of the power grid. Where does that energy come from? Well, here's a breakout within the US. Mainly, the number one is natural gas, about 38%, followed by coal. Nuclear is about 20%, and then finally renewables. And what we're really trying to do here is we're trying to build out the renewables, phase out natural gas and coal. Nuclear is going away, possibly coming back with future generations of nuclear power plants, but existing nuclear power plants are being phased out. So we really need to grow the renewable part of that, and that's where wind comes into play. So we're going to talk now about the technology of offshore wind power, and going to start by showing this U.S. wind resource map. So what this is depicting is areas that are good for wind production with wind turbines, and it ranges from fair, which is this color here, all the way up to superb, which is the blue color here. Now, this is not a map of how strong the wind is. This is a map of how good the wind is for wind turbine production. It's kind of like a Goldilocks zone. You don't want the wind too weak. You don't want the wind too strong. You want it kind of in a mid-range there. And also you want the wind to be consistent. You want the wind to be, blowing, consistent amount of time. And when you plot it that way, you find that there is a lot of wind resource in the coastal waters of the US within our exclusive economic zone, which extends out 200 nautical miles. As a practical matter, wind farms need to be sited within about 50 nautical miles from shore, but you can see all around the entire coast of the US, including particularly in California, in our region, there is a lot of strong and very useful wind resource. In fact, if fully developed, the offshore wind power available to the US within our EEZ would produce about twice as much electricity currently on the US power grid. So that's a lot of resource out there. So let's start out now by talking about some terminology here. So this is an offshore wind turbine, and let's talk about the different parts. This is called the blade. There's typically 3 blades here. The blades come together in the hub. This assembly here is called the nacelle. This is the tower. This is the deck. Floating substructure here. Air gap refers to the distance between the bottom of the blade and the surface of the water, and that's important. We'll come back to that. So let's take a look inside the nacelle of a floating wind turbine. And first of all, what you need to know is, unlike a regular windmill, it doesn't position itself based on automatically the wind makes it turn. There is a yaw system. There's a yaw assembly here, and there's a large electric motor which turns this whole assembly to be facing into the wind. And that's based on what is sensed by meteorological sensors on the nacelle here. So as the wind direction changes, the turbine automatically, using this yaw system, changes to face the wind. As the wind speed changes, the turbine automatically uses its pitch adjustment system to change the pitch of the blades to get optimum power out of the wind. And also, as the wind becomes above a certain high-speed threshold, the pitch will be reduced such that it will control the rate of spinning of the blades. These large offshore wind turbines don't turn very fast. A maximum rotation rate is about 8 RPM, which means it takes a little more than 7 seconds for the blade to make a full rotation. And you might think, well, it's kind of slow, it looks kind of lazy. But the blades are so large, as we'll learn in a minute, that the tip of the blade is actually moving about 200 miles an hour. So they're really huge. But as the wind picks up, they'll control the pitch to make sure the rotation rate doesn't get above about 8 revolutions per minute. This is the generator, and the latest generation of offshore wind turbines use what's called direct drive. That means there's no gearing assembly here or anything like that, but rather there's just one big giant generator here, and it's kind of works like this. Inside this drum here, there is coiled wire, and on the outside of the drum, which rotates relative to the inside core here, there are very, very powerful permanent magnets that are oriented this way. And as the magnetic field, of course, is changed going through the coils of wire, that generates electricity. It's direct current. That DC electricity then goes into this power converter system controller, and it gets converted to AC, actually 60 cycle AC at very high voltage. The standard voltage coming off an offshore wind turbine is 66 kilovolts. That's 66,000 volts, three-phase electricity at 60 cycles. So that's kind of what it looks like. Oh, by the way, there's a braking mechanism here. In high winds, the blades are actually feathered, and the braking mechanism is applied, and the blades no longer rotate. Now, the thing that's really distinguishes offshore wind turbines from their onshore cousins is their size. They are absolutely huge. The ones here above the blue here are offshore turbines. For the Morro Bay project, I'm expecting it'll probably be about a 14 or 15 megawatt system. So it's going to look pretty much like this one right here. And to put that in context, here is the Washington Monument. We're talking about a tower that's at least as high as the Washington Monument, possibly higher. Over here is the Airbus A380 drawn to scale. This is the world's largest airplane. It is dwarfed by the size of these wind turbines. Why are they being made so big? Well, bigger is better. And the reason is the power from the turbine is actually proportional to the rotor swept area, which is sort of the size of the circle where the rotor rotates here. Going back to your high school math, you remember that the area of a circle is equal to pi r squared. Well, r in this case is the length of the blade. So if you double the size of the turbine, double the length of the blade, you don't get double the power, you get 4 times the power, because 2 squared is 4. If you triple it, you get 9 times the power, because 3 squared is 9. It's actually better than that, because as you build the turbines higher, they reach higher into the atmosphere, and the wind is generally increasing up there in the atmosphere. So why don't we just build turbines on land bigger and bigger and bigger? Well, we pretty much hit the limit of land-based turbines. And I think the limit right now is about 2.5 megawatts compared to 15 megawatts were being planned for offshore. And the reason is you simply get to a point where you can't transport the blades on highways anymore. Now, you can break up the tower into multiple sections. You can transport it on the highway. You can transport the nacelle on the highway. But the blades have to be built in one continuous piece. No one has figured out a way to make a blade in multiple sections because they're under so much stress. They got to last 25 years. The blades are made in one continuous piece of material, and you simply can't transport blades this large on the highway. Can't be done. How are they transported? Well, they're transported by sea. They're actually built on a factory that's right at the seaport. And when the blade is done, they open up the factory door and they move it, just a matter of a stone's throw away, and load it on the ship, and then they transport it. So it's built that way. And that's the fundamental limitation on the size of land-based turbines compared to offshore wind turbines. Now I want to show you this power curve for a typical wind turbine. So what we're looking at here, and this is pretty instructive, this is on this axis, we're looking at turbine power in megawatts as a function of wind speed in meters per second. Now I'm going to be talking in terms of miles per hour. So just double this meters per second, and that's roughly the wind speed in miles per hour. And what you see is from 0 out to about 7 miles per hour, there's zero power produced by the turbine. That's because the blades just aren't turning. There's not enough power there to make the blades turn. And then once you get over that threshold, about 8 miles an hour or so, suddenly the blades start turning, and the power increases very rapidly. It increases in proportion to the cube of the wind speed, up until you get to about 20 miles an hour, up in the range of about 20, 22 miles an hour. That's the max, that's kind of the sweet spot. And what happens at this point is the turbine automatically reduces the pitch of the blades to maintain a constant rotation rate. And at that point, the turbine is producing its maximum power up to a point where the wind gets up around 50, 55 miles per hour. And basically the turbine shuts down by feathering the blades and engaging the braking system, and the power drops to zero until the wind speed comes back down low again. If it didn't do that, if it didn't control the rotation rate, the blades would fly apart and the whole thing would destroy itself. So this maximum power here in the sweet spot, so to speak, has a particular name, and I'd like you to remember that it's important. It's called the nameplate capacity, or the rated capacity of the turbine. On that prior chart, we were looking at 15 megawatts and 6 megawatts. Well, that's the rated capacity, or nameplate, or nameplate capacity. Now, in the long term, the turbine is not always operating up here in the sweet spot. Sometimes it's down in here. Sometimes it's not producing power at all because the wind is gone. Sometimes the winds are too high and it has to shut down. So there's something called the capacity factor, which takes that into account. And the capacity factor is basically the ratio of the long-term, or for example, annual average power produced by the turbine to its nameplate capacity. For land-based turbines, the capacity factor is typically 30 to 40%. So you might have a 1 megawatt land-based turbine, but in the long-term average, it's only producing about 30 to 40% of that. The capacity factor for offshore wind turbines are much higher, typically about 60%. And that is mainly because, as I mentioned earlier, the winds offshore generally are more consistent and blow more steadily than the winds onshore. And so the turbine will be operating in its optimum capacity more often. So let's talk about these offshore wind turbines. They basically fall into two broad categories: fixed bottom and floating. So here's what a fixed bottom looks like. You might have a monopile here, which is basically embedded directly into the bottom, 4-leg jack, again, embedded directly into the bottom. All of the existing offshore wind turbines in the United States are fixed bottom wind turbines, and they exist off the East Coast. There's a fair number of them off the East Coast. Well, the problem there is they only work into depths of about 60 meters. And as a result, they will not be a player in California. In fact, they will not be a player anywhere on the West Coast because the water just drops off too fast. So if you can forget about fixed bottom. Any wind turbines off the West Coast of the US are going to be floating wind turbines. And there are basically sort of three categories there. And that has to do with the mooring, essentially. There's something called tension leg platform, which is something we would want to use if you need to keep the wind turbine fixed in place as opposed to moving around. There's something called spar, and the problem with that one is difficult to deploy because they're unstable until they get rigged in place. There's the spar buoy, which is really good for heavy winds and sea conditions. Wind turbine based on a spar buoy can withstand a hurricane. Hurricane can run right over this, no problem. Very, very stable. The problem with spar buoys is they have a very deep draft, and there are not many harbors that can handle the deep draft of a spar buoy. So in my judgment, neither tension leg platform or spar buoy are going to be a player in the Morro Bay project. In fact, I'm almost certain the Morro Bay will be based on semi-submersible design, which looks something like this, using a catenary mooring configuration. So what is a catenary mooring? Well, a catenary mooring basically is typically 3 lines coming down from the turbine, and they basically just hang down and kind of splay out here, secured to a drag embedment anchor. And this is sort of an angled steel plate that's pulled in, embedded into the bottom by a tugboat, typically embedded down to a depth of about 30 feet. About half, the first upper half of the mooring line is typically synthetic mooring line, like big thick nylon line. And the lower half of the mooring line is heavy steel chain. And the mooring lines generally have to be at least twice the water depth. So for the Morro Bay Wind Farm, the average water depth is going to be about 3,000 feet. So the average mooring line length will be about a mile. Now, associated with that, there is the concept of watch circle. So the point here with that type of mooring, the turbine doesn't really stay fixed in one place. It actually drifts around based on the wind speed. So for example, let's assume this is the coast of California here and the wind is coming out of the north. Well, the turbine would have drifted down to the south end of its watch circle. If the wind suddenly switches around to the south, the blades will turn and face the wind and the whole thing will drift up to the north end of its watch circle, and similarly east and west. For the Morro Bay Wind Farm, based on the water depth and everything, I'm estimating the diameter of the watch circle will be about 2 or 3 football fields. So these things, it's going to be fairly dynamic. They're going to be moving around in a circle of about 2 or 3 football fields diameter. So what about the electrical cables? Well, here's a typical electrical cable layout for a floating wind farm. Looking down from above, you might think, well, what do we just pack these turbines in there? Well, you can't really do that because to maintain efficiency due to wake turbulence coming off the blades, you have to space them apart, typically about 8D in the crosswind direction and about 10D in the prevailing downwind direction, where D is the rotor diameter. Now, this means the turbines in the Morro Bay Wind Farm will be a little bit more than a mile apart. Now, the array cables here, the dots here depict the location of the turbines, and the lines here are the array cables that connect them together. They will be partially suspended above the ocean floor, connect the turbines to each other and to a floating offshore substation. Here's the substation depicted here. They'll carry 66,000 volts of 3-phase 60-cycle AC electricity. They will all come together in the offshore substation. There it will be sent ashore via what's called an export cable, which will be buried under the seabed. And it will bring the power ashore at Morro Bay from the offshore substation at a voltage of 132,000 volts. So here's what that would look like in cross section. What we're depicting here are only the dynamic array cables that carry the electricity. I'm not showing the mooring cables. And it would be something like this. The cable would come straight down. There would be floats here that actually, this is called the lazy wave configuration. There are floats here that suspend it about halfway in the water column. Then it's grounded here, comes back up, more floats, goes up to the next wind turbine, and et cetera. They're all connected together. Eventually, they terminate in the floating offshore substation and upgraded to 132 kilovolts. Then it goes into the export cable, which is buried below the seabed, comes ashore. It's going to be coming ashore at the Morro Bay power plant, which is a decommissioned power plant very similar to Moss Landing. It's not producing power now, but it does have connections to the grid. So it's the ideal place for this power to be brought ashore and then be placed onto the power grid. Here's what an offshore floating substation might look like. This is an artist's rendition. The one for the Morro Bay farm may be bigger than this, but this is kind of what it would look like. So what do you need to field such a capability in terms of port infrastructure requirements? Well, you need a wharf, a really big wharf that can handle about 6,000 pounds per square foot and a really strong pier strength. You need a navigation channel or a port that has a deep enough draft that you can tow the turbine out from there, because you're going to assemble the turbine at the wharf side right here. You need an upland yard to store the components of the turbine. You need a really big crane, 400 to 600 ton lift capacity, maybe even larger for the ones we're talking about. And of course, you're using that crane at wharf side to assemble the turbine. And then, of course, then you need some vessels for crew access maintenance, for towing the turbines out to sea and for doing maintenance and that sort of thing. So where is this going to be for the Morro Bay project? My guess is it's going to be Port Hueneme. Port Hueneme, I believe, meets all of these criteria. Port Hueneme is in Ventura County, about 40 miles south of Santa Barbara. If Port Hueneme doesn't work, I think you're going all the way south to Long Beach, which is pretty far down there. So I'm pretty sure Port Hueneme is probably going to be the target facility. What's it cost to fill one of these things? Well, here's a cost breakdown for a typical floating offshore wind farm. The big three components of costs are the turbines, the substructure and foundation, the floating substructure, and finally the electrical infrastructure. Those three components comprise about 3/4 of the cost of the entire wind farm. Surprisingly, assembly and installation is not that much, less than 10% here, and then various other costs here. So what is the Morro Bay project going to cost? Well, my rough estimate is $30 to $40 billion. This is a big deal, $30 to $40 billion. And that's a rough estimate, but based on what others have costs and kind of where the industry is going, that's, I think, pretty much in the ballpark. That's certainly just my estimate. So let's talk about cost here and what the electricity might cost. from this power plant. And the way to look at that is in the context of this quantity called levelized cost of energy, LCOE. LCOE is, it can be regarded as the minimum constant price at which electricity must be sold in order to break even over the lifetime of a power plant. So you take into account all the costs to design, build, implement, maintain, operate, and even decommission a power plant over its X number of years lifetime. You take that cost and then you divide by the total amount of power produced by that plant, and then you get this levelized cost of energy. So you can see that when, and by the way, this is depicted in terms of dollars per megawatt hour. We often think in terms of cents per kilowatt hour, because that's how our PG&E bill comes. Well, you can convert that really easy just by dividing by 10. So for example, onshore wind, average across the entire world, has a cost of $46 per megawatt hour, which works out to 4.6 cents per kilowatt hour, which is quite good. It is by far the cheapest energy on the grid right now, followed by solar. Solar will soon surpass wind because solar prices are still continuing to come down. Natural gas, geothermal, offshore wind is here. And notice it's pretty expensive compared to onshore wind. Then coal, and then finally nuclear sticking out like a sore thumb here. One of the big problems with nuclear, it's the most expensive power on the grid by far. So you may be concerned about this high cost of offshore wind compared to, say, onshore wind. Well, the main reason that's true is, and it's about 10 cents per kilowatt hour compared to 4.6 per kilowatt hour for onshore wind. That's mainly because offshore wind has not yet achieved the economy of scale associated with onshore wind. As offshore wind farms are built out to utility scale is usually defined by 600 megawatts or greater, their costs will decrease and approach those of onshore wind farms. So the projections are that the cost of offshore wind is going to come down and approach that of onshore wind. It's more expensive to deploy an offshore wind turbine, but they are more efficient and they produce more power. So it kind of compensates. And ultimately, once they're built out to grid scale, utility scale, the price will come down such they will be some of the cheapest power on the grid. So what are some examples of floating offshore wind farms? And there's lots of examples of fixed bottom offshore wind farms, even in the US, quite a few in Europe as well, quite a few in Asia. But there are really only two floating operational wind farms in the world. Now, there's a number of individual floating wind turbines that are sort of one-off prototypes around, various countries. But in terms of commercial floating offshore wind farms, there's really right now only two. The first is High Wind Scotland. It was deployed off the coast of Scotland in 2017, and it produces 30 megawatts of electricity. It uses the spar buoy here. You can recognize that. The second is Windfloat Atlantic. It was deployed off the coast of Portugal in 2020 and produces 25 megawatts of electricity. It uses the semi-submersible structure, which you recognize from our previous discussion. So the wind farm off Morro Bay is going to look pretty much like this. But one thing to be aware of here, these are very modest compared to what Morro Bay is going to produce. These are like a factor of 100 less than what Morro Bay will produce. One thing I want to get across to you on this talk is this is a huge, huge project, and it'll be a huge system. So now let's get into the Morro Bay Wind Farm, the specifics of the planned project. So first of all, where is it? Well, here's where it is. And take particular attention to the hatched area here. There's various different colors drawn on this map. That has to do with different proposals that were proposed and shot down. What finally got approved, and the final thing is this hatched area here where these lines go here. So to put that in context, here's Morro Bay, here's Cambria, here's Lucia. So although it's called the Morro Bay Wind Farm, it really isn't off Morro Bay. It's north of Morro Bay. It's off the coast of Big Sur between Lucia and Cambria, about 20 to 30 miles offshore. It abuts the Monterey Bay National Marine Sanctuary, which is this blue area here, but it does not go into the sanctuary. I'm sure there must be some language in the sanctuary language that says, you can't do energy production in there. And so as a result, it comes right up to it, but it does not go into it. Here's the 1,300 meter depth contour. So you can see it's actually in very deep water. I think the average depth is probably about 1,000 meters for this wind farm region. So let's talk about the capacity here. There's enough room out there for 400 wind turbines spaced about a mile apart. The area of the region, by the way, is 399 square miles, so it's quite big. I'm saying 375. They've talked about 350 to 400, so I'm splitting that difference and saying it's going to have 375 wind turbines spaced about a mile apart, each with a nameplate capacity of 14 megawatts. Now, there's no 14 megawatt floating wind turbines on the market right now, but they're going to be soon. And in fact, by the time this system is deployed, 16 and 18 megawatt systems are also very likely going to be out there. But I'm assuming 14 megawatts for the purpose of various calculations here. And with the capacity factor of 0.6, 375 wind turbines, 14 megawatts, capacity factor of 0.6, you can check my math. It will produce in the long-term average 3,150 megawatts of power, or 3.1 gigawatts of power, which is about 10%, by the way, of the Biden administration's goal by 2030. The goal by 2030 for the Biden administration is 30 gigawatts of offshore wind power by 2030. Well, this is going to be about 10% of that. So that's how huge it is. In fact, when it comes into operation, it will be the highest capacity power plant in the state of California. Now, for reference, 1 megawatt is enough power to support about 650 average sized homes. So the wind farm will provide enough power for about 2 million homes in the long term at a likely cost of about 4 to 6 cents per kilowatt hour, which will be very competitive. So here's a rough timeline of the project. Stress the word rough here. I made this up and I'm making some assumptions and they may not hold, but basically the project was approved by the Biden administration, approved in the sense that the Department of Interior gave approval to go to the next stage of basically auctioning off the rights to this development of this system. That will happen in 2022. As I understand it, there are about 14 companies currently expressing interest. I don't know exactly how this process works, but I think it's very similar to the way that offshore oil leases are auctioned off, some type of auction process. And could be more than one company winning it. One company may bid on the northern part of the domain, another company may bid on the southern part of the domain. They split it like that. Companies may form, coalitions together. So that should happen next year. And then we'll go into a design and permitting phase, which I'm assuming here is going to be 4 years, but it could be much longer. It could be as long as 7 years. And then during this phase, the company that has won the lease basically will come forward with the design of what they plan to do out there. And the Department of Interior will have to review that and give them a permit to proceed. That's the period of time where public comment would come into play. Lawsuits almost certainly will be played out. Federal judge might decide in favor of a lawsuit and put a stop to the project or put a hold on the project until that is resolved. So that's the kind of things that will happen during this 4-year period. It could extend longer. But if this optimistic view of 4 years for design and permitting holds, and that means deployment would begin in 2027. I'm estimating it'll take about 3 years to build it out. And that means it would be fully operational on the power grid by 2030. And lifetime design life of about 25 years for each turbine. So that means beginning about 2052, you begin replacing wind turbines at the end of their life cycle. So that's kind of an overview of the technology. That's an overview of the specifics of what's planned for Morro Bay. In terms of what's planned for Morro Bay, pretty speculative there. I'm just looking at the technology and saying this is what I think it's going to be. I haven't seen any bids or any designs or anything like that, but I think what I've laid out here is pretty close to the way it's going to ultimately go down. So now, what are the possible issues of concern? Well, from my viewpoint, they kind of fall into 4 areas. Impact on commercial fishing, impact on whales and dolphins, impact on seabirds, impact on the Big Sur Viewshed. So let's start first with commercial fishing. Commercial fishing will be banned within the entire 399 square mile area of the wind farm, as towed nets would certainly be in jeopardy of becoming entangled with the mooring lines and electrical cables in the water. Just not going to be able to fish in there. On the positive side, the wind farm will effectively serve as a very large marine protected area and a habitat for many types of fish. Thus, it will help rebuild and sustain fish populations in the surrounding waters. The Pacific Coast Federation of Fishermen's Associations has come out in opposition to the wind farm. They don't want to give up that large chunk of real estate out there for fishing. And I can see their point. I want to say one thing about fishermen. I have a great respect for them. They put food on our table. They pursue a very dangerous career. So their voices need to be heard. There's no doubt about that. And they have come out in pretty strong opposition to this project. Impact on whales and dolphins. Well, let me say up front, I am not a whale and dolphin expert by any stretch of the imagination. There are a number of world-class whale and dolphin experts in our area, by the way, but I'm not one of them. But I'm just going to tell you, just from sort of, basic common sense here, I think there's basically three areas of concern. The first is the possible impact of noise in the water from the turbines. Second is possible impact of physical encounters with the mooring lines or dynamic electrical cables. And the third is the possible impact of electric and magnetic field EMF emissions from the dynamic array cables, which are going to carry all this huge amount of voltage and electricity. So let's first begin by taking a look at the migration zone for gray whales. This area in pink here depicts the migration zone for gray whales, but it's not, they mainly are much closer to shore. The vast majority of gray whales migrate within about 6 to 7 miles from shore, as I understand it, but you may find some as far offshore as 20 to 30 miles. So how does the wind farm play into that? Well, the wind farm is right here. So what you can see is, most of the whales are migrating kind of in this band here. They're not going to be transiting the wind farm, but it's inevitable that some whales and dolphins will find themselves out here in the vicinity of the wind farm transiting it. So we certainly can't say that there's not going to be some impacts on whales out here, but at least in my judgment, I don't think it's going to have a major impact on the general migration of the gray whales. So, as I mentioned, there are three areas of concern. The first is noise put in the water by the turbines. Now, these turbines do produce a lot of noise. Just the blades turning around produces a lot of noise. That noise will travel through the atmosphere, hit the ocean here. Some will go down into the water, but mostly reflected off. But I think the real concern is going to be vibration and noise that transits down the tower into the floating substructure and then propagates out into the ocean. And it's going to be low frequency noise associated with the turning of machinery, associated with vibration of the spinning turbines and so forth. And how will that affect the whales? I don't know. It's not going to be a large amount of noise. I mean, I'm certain that the amount of the decibel level from a wind turbine here is going to be much less than that of a ship. On the other hand, there's 375 of them out there, spaced a mile apart. So what's going to be the effect of all of that? Well, can't really say at this point, but it's something we need to think about, something we need to be concerned about. The second area of concern is physical obstruction caused by electrical cables in the mooring lines. Here's what the array cables look like. You can see they're pretty hefty cables here. Here's a guy holding one. Here's what it looks like in cross section. And here's what the mooring line looks like. Here's a human here. Here's the mooring line. You can see it's a pretty big line. So there's a lot, and there's literally thousands of miles of these cables and mooring lines in the water for this wind farm. It's so huge. The good news here is that the maximum depth for most whales in terms of the depth they dive to is about 700 feet. Dolphins only about 150 feet. So that will be well above the area where things splay out and get complicated. And pretty much what whales and dolphins would see would be these cables coming straight down below each wind turbine. And of course, they have sonar. They can pretty easily avoid these cables. So I don't think it's going to be a big issue, but it is something to think about. And the final area of concern is electric and magnetic field emissions from the electrical cables. This is what the cable looks like. We've seen this picture a couple of times. The cables have a very double layer of armoring around here. They're heavily insulated. They're well grounded. And as a result, there's going to be no leakage of electric field out of these cables. However, the concern is induced electric field. Because of the insulation, the grounding, as I mentioned, the electric field really is confined within the cable. However, you can't stop the magnetic field from being emitted. There's no way to shield the magnetic field. So there is a magnetic field that's going to be around each cable. That magnetic field will be fluctuating as the current changes direction 60 times a second. The orientation of the magnetic field will change 60 times a second. When you have a changing magnetic field in the presence of a conductor, that produces an electric field. That's how a generator works. And so the concern is the fluctuating magnetic field around the cables will produce and induce electric field out here. Now it's going to be weak, about 10 to the minus 5th amps per square meter at a distance of 10 meters. So for example, if you're a diver and you come right to this cable, you're not going to notice anything. On the other hand, if you have instrumentation that measures electric fields, you'd be able to measure it. You'd be able to measure it tens of meters away from the cable. How will that affect marine life? Well, here is what the Bureau of Ocean Energy Management says. Basically says, we don't really know. More research needs to be done. Synthesis of available data and information clearly demonstrates that more work is needed to understand the nature and magnitude of any potential impacts of marine species from undersea power cables, electric and magnetic fields. So that is a concern. The fields are very weak, but marine creatures are known to respond to very weak electric fields and even magnetic fields. So that, again, an area of concern needs to be looked at. So in terms of summary, at least from my viewpoint, others may come to a different conclusion, and that's fine. The safety and well-being of whales and dolphins is important to many people, and the proposed Morro Bay Wind Farm does raise issues of concern. Opinion on this matter should be guided by science, of course, but there is little, if any, science to draw on. And the reason that's true is because there's really no comparable wind farm out there, floating wind farm out there anywhere in the world, comparable in size to what's planned for Morro Bay. As far as I can tell, at least as of now, whale advocacy groups have not yet taken position on offshore wind power. So that's kind of where we are on this. Final area or next area of concern is impact on seabirds. Millions of seabirds exist off the coast of California, and the area that will be occupied by the wind farm is certainly part of their habitat. Unfortunately, wind turbines do kill birds, but there is technology to reduce the number of kills. And for example, there's bird detection radar. This radar can actually see birds about 5 miles away, and it can track them automatically. And if they're heading towards a wind turbine, it can automatically shut the turbine down until they pass. So that could certainly be deployed at Morro Bay. Also, it turns out that painting one turbine blade black, just simply doing that, has been shown to reduce bird kills by about 70% in land-based turbines. So that's a good thing, and that's an easy technology to employ. And finally, seabirds tend to fly close to the surface, unlike terrestrial-based birds. They have no reason to fly at great altitude because their food source is at the surface. They're not flying over terrain. So it's very likely that most seabirds will fly under the rotor. Remember, we talked about the air gap. They'll fly under the rotor. They'll fly in the air gap under the tip of the rotor blades and be safe from that. In any case, the Audubon Society supports offshore wind development, recognizing that climate change is killing many, many more birds each year, and that offshore wind power is part of the long-term solution. And the final area of concern is impact on the Big Sur Viewshed. So I'm going to share this handy dandy little equation here with you, which says that the distance in miles that you can see something offshore above the horizon is equal to 1.22 times the square root of the height of that object above the sea surface plus the square root of the height of your eye above the sea surface. So the Morro Bay Wind Farm is located 20 to 30 miles from shore. Many of the turbines will be visible from Highway 1 under optimum viewing conditions because, the hub height will be about 600 feet. If you're driving down Highway 1 Big Sur, you're about 400 feet above sea level. You put those into this equation, you find out that your horizon's about 42 miles away. So the wind farm will be within the horizon. However, you're going to have to look hard to see them because they will appear as specks on the horizon. Also is going to require optimum conditions. Under hazy conditions, you're not going to see them. Evening conditions, when there's glare off the water, not going to see them. In the morning, when it's clear, you're going to be able to see them. And this is what it's going to look like. You have to look very close here. This is the view. This is a simulated view of the wind farm from Julia Pfeiffer Burns State Park in Big Sur. And if you look very closely, you'll see some dots right along here on the horizon. That basically is the wind farm. This is what it would look like to you with the naked eye on optimum conditions. This simulation was produced by the Bureau of Offshore Energy Management. Now that's what it looks like with the naked eye. Will that bother people? Well, it's not going to bother me. It might bother some people, but it's not going to bother me. Here's what it looks like with a modest pair of binoculars from, again, Julia Pfeiffer Burns State Park. With a modest pair of binoculars, you'd actually be able to see the blades turning. Will that bother people? Not going to bother me. I'm actually going to feel pretty good looking out there and thinking, gosh, we're getting all that free green energy here, but it may bother some people. So that's putting that on the table. So last slide, summary, and then hopefully plenty of time for a question and answer and discussion. We face a climate crisis that is growing worse by the year. And you probably saw in the news just last week, the executive summary from the Intergovernmental Panel on Climate Change, IPCC. Sixth assessment report came out, just the executive summary, and it created quite a stir, created a lot of press interest, and just shows that things are actually getting worse faster than we thought. Offshore wind power is a key technology for reducing CO2 emissions and mitigating this crisis. The Morro Bay offshore wind farm was recently approved by the Biden administration to move forward, at least to the leasing and permitting phase. Deployment of this massive wind farm will likely begin in about 6 years and be complete by 2030, at which time it will become the largest capacity power plant in California and provide enough carbon-free electricity to power at least 2 million average-sized homes. Although there are areas of concern, in my judgment, none of these concerns are showstoppers for this project. Others may come to a different conclusion, and that's fine. I believe the Morro Bay Wind Farm should be deployed and that its successful implementation will serve as a model for other offshore wind projects in the US and in the world aimed at fighting climate change. So that's it. I'm now going to stop the share and open it up to question and answer.
Thank you, Mike. Jim, did you have a question? Turn your mic on. You're muted.
In New England, there was a lot of controversy involving high political people against the visual picture that they see. I never saw why that was such a big issue. Is there any data that sort of tries to put a picture on what group of people might protest the visual experience?
Yeah, in New England, those wind turbines are bottom mounted and they're much closer to shore than we're talking about here. So people definitely see them. They see them. They're big. They're close to shore. It's a matter of personal taste. It's a matter of how you feel about looking out over the ocean. Most people want to see a pristine environment. It's not you don't look out there and see an oil rig. You don't want to look out there and see things like that. So I predict there are going to be people who are going to be concerned about this. But the fact of the matter is, for the Morro Bay project, the wind turbines are far enough from shore that, like I said, you're going to have to look hard to see them. You're going to be able to see them, but you're going to have to look really hard.
Don't forget the group that just really likes to see those things twisting out there.
Well, I kind of am in that category. I mean, I'm going to look out there. I'm going to feel good about knowing the technology and knowing that it's green energy and it's replacing coal-powered and gas-fired power plants. Others may not feel the same way.
Yes. Yeah, Jim. Oops.
Has anybody calculated how much this will replace the Diablo Canyon nuclear plant?
Well, yeah, Diablo Canyon, yes. Yeah, right now, this is going to be larger than Diablo Canyon. Diablo Canyon, I think right now is about 2.5 megawatts. And it's going to shut down completely by 2025, I believe. There's 2 more reactors that are going to be shut down. The Diablo Canyon is the last nuclear power plant in California. When it shuts down, we're going to lose about 2.5 about 2,500 megawatts. But this one was going to produce over 3,000 megawatts. So this is larger than Diablo Canyon.
Thank you.
You didn't talk about sea lanes, the impact on shipping.
Oh, that's a good question. That's a very good question. There will be lights on these things, and there'll be flashing lights and they'll certainly be very visible by radar. So if any ship comes in there and has a collision with these, it's going to have to be they're going to have to be messing up pretty bad. I mean, they're going to be visible, from lights. They're going to be very visible on radar. They're going to be highly, depicted on mariners' charts and so forth. But that doesn't mean a ship might not find its way in there, lost in, some malfunctioning navigation system. It's possible that could happen, and there could be a collision. And that's just something you just have to hope against.
Does the area lie in sea lanes?
No, it's not in a shipping channel. It's not an area of high traffic. It is an area that fishermen go, that's for sure. It is an area that the Navy has used for training. And in fact, the last holdout in the government for giving approval for this was the US Navy, because they have to give up training area there. You're no longer going to be able to sail a submarine through that part of the ocean. And the Navy was objecting to that, but finally they gave in and is moving forward.
Okay, Doug, Wilhelm, unmute yourself. You need to unmute, Doug.
Oh, we all forget.
Yeah. Oh, you're still muted. I can't.
There we go. I understand that the span of these things is like bigger than the span of the wings on a large airplane.
By far.
And pardon?
By far, they're much larger than the wings of the largest airplane.
Yeah, and they're made out of balsa wood, and there's a real scramble to try to find balsa wood that's big enough, because they can't be patched or anything. It's got to be single pieces.
Well, the wind turbines we're talking about, the ones that are planned for this project, it won't be balsa wood. It's a carbon carbon fiber laminate kind of material. They're actually pretty. I mean, they're so huge. They weigh many tons, but they're actually fairly light. It's lighter than, it's not steel or anything like that, but it's a continuous carbon fiber kind of thing. Yeah.
George. Yeah, George.
Mike, how many hours a day will this be producing energy? Are the winds sufficiently spread out over the day cycle, or are there going to be times when you expect that they will be down?
The winds over the sea are much more consistent than the winds over land. And one reason there is, over land, we have a diurnal cycle. It gets hot during the day, and you get thermals that are going up and bringing wind down from the higher atmosphere. Then it gets cold at night, and the land cools down, and that makes the boundary layer very stable, and it kind of cuts off the surface from the upper atmosphere. And as a result, the winds tend to get weak at night. They're stronger during the day. That doesn't happen over the ocean. There isn't much diurnal variation of the sea surface temperature, and as a result, the winds are much more consistent between day and night. Now, there will be periods of time when a big high pressure system comes over and parks right over the wind farm, and the winds are very light, and the ocean's very glassy. Man, it's going to go down to zero. It's not going to be producing power. That won't happen that often, but it will happen sometimes. There'll be other times when a big storm hits and the winds are, for a brief period of time, are greater than 50 knots or so, and it's going to shut down. So there are going to be these periods of shutdown. The capacity factor is expected to be about 60%. So on the long-term average, producing about 60% of 14 megawatts per wind turbine. But there will be periods of time when it is producing zero power. I mean, it'll be fairly rare, but it'll happen. But, the same is true of any power plant. Various power plants have to get shut down temporarily for maintenance and that sort of thing.
I think
Marlene had a question.
Well, I think it's nearly been answered. I was concerned about what it would happen during really, really big storms. And maybe we'll even get so far as having a hurricane that far north at some point, but who knows?
Yeah, like I said, the most likely floating substructure is going to be the semi-submersible kind. And I'm not sure they would be able to survive a hurricane. The worst case scenario, it would capsize. It's probably unlikely to be that spar buoy thing because that's a lot of logistics associated with putting that together. Yeah, that's something that's what the engineers have to figure out. They got to look at what's the once a century kind of wind speeds expected out there. We have to kind of design to that.
Brooks?
Mike, one of the assumptions I saw on your chart was that the cost of these offshore wind farms has to come down to more or less equal the onshore. But I'm presuming that solar is going to be coming down dramatically in that period too.
Yes.
Why could we not just mandate that all new construction has solar panels on the roofs and get to an equivalent result?
Well, I think that's a great point. And I first of all, you're absolutely right. Solar is just coming down. It's going to continue to come down. It's kind of like, the way computer chips kept getting cheaper and cheaper, solar cells are getting cheaper and cheaper. Right now, my roof is being replaced, and next week I'm getting solar panels here. So I'm way on board with that whole concept. Eventually, solar will be the cheapest. There's no doubt about it. But I think wind is a nice complement to solar because, of course, you don't get solar power at night. And as a result, you've got to go to battery storage and that sort of thing. By the way, we have one of the world's largest battery energy storage systems at Moss Landing now operational, which is really great. And there's another similar system being planned down at Morro Bay. That's all good, but it's good to complement that with other forms of energy that helps get you through the night. And that's kind of what we do with wind power. Right now, California leads the country in solar. We have such a tremendous excess of solar power during the day that we give it to other states. In fact, we don't just sell it to them. We don't give it to them. We pay them to take it from us. We pay them to take it from us. We have such an excess. That's what a guy from PG&E told me. And, way to get around that is battery energy storage, but also, complementing the solar with wind, I think is helpful too.
Jim?
Is there any value in having storage for generation in order to deal with the fluctuation, or that's not enough to justify the storage?
Well, that's a good question. I think that's a possibility. And as I mentioned, they do have a big battery storage system. I'm not sure exactly where it stands, whether it's operational yet or not, just planned, but down in Morro Bay area. Congressman Panetta and Congressman Carbajal, who's down in that district, have kind of collaborated together to help move the Morro Bay project forward. And their general vision is creating in Central California, so along the Central Coast, a leadership in terms of renewable energy. And so that would fit well into that concept.
George?
I'm trying to figure out who's going to develop or build the turbines, because I think that the leaders right now are Dutch manufacturers or Chinese manufacturers. Is there any American engineering firms or manufacturing firms that are likely to bid or win on these?
Yeah,
projects?
well, there's sort of two things. There's the company that would bid to lease, and then there's the company that would actually sell the turbines to that parent company, to that overarching company. The companies that there's a couple of companies in California that have expressed interest. There's a couple that are based up in the Bay Area. In terms of the companies that build the turbines, General Electric is one of the leaders, as is Siemens, a German company. So GE is a definite leader, but they actually build the turbines in France. They build them overseas. But good point. Where are these turbines going to be built? I predict that, assuming this project goes forward, that some company like GE or Siemens or some other company will open a West Coast, West western coast of North America. I'm not saying it's necessarily going to be in the US, but some kind of manufacturing facility somewhere on the west coast of North America to build these turbines, because right now they're being built in France, and it's just not efficient to ship them all the way from France. So if you're going to build them, maybe you had a facility in Mexico or Central America or California, and then it's much more cost effective. So once this thing starts to go forward and it's clear it's going to actually happen, I think you'll see companies like General Electric or other companies open factories on the West Coast.
George.
What, two things, Mike. What do your feasibility study indicate that who's going to pay for all this? It's going to be financed by the government or private sector?
Great question. Certainly, it's going to be financed by the private sector. However, there was just announced, just a matter of I got some notes here on it, just a matter of last week, there was announced a bill before Congress, which is called the Offshore Wind Manufacturing Act, which was introduced by Cory Booker, Ed Markey, Robert Menendez, and Elizabeth Warren. And it would create a 30% investment tax credit for qualified facilities that manufacture offshore wind components and subcomponents. And it would also implement a production tax credit that ranges from 2 to 5 cents per watt, multiplied by the total rated capacity of the turbine. So there are basically tax incentives that are being proposed in Congress right now, which would facilitate this going along. And that's very similar to the tax credits that have gone to the oil and gas industry for decades. But generally speaking, it'll be private investment. There'll be some company that's going to say, we've worked the math out here. We want to borrow the money from a bank, and we're going to give you a return on investment. And that it'll be, going forward with private investment. However, the tax incentives as proposed by this this Offshore Wind American Manufacturing Act will certainly change the equation in a more positive way.
I don't want to put a negative downside comment in, but my experience, lifetime experience now in locating aquaculture ventures along the coast of California particularly, would indicate that a 7-year period to get permits and to get through all the litigation that's going to happen and everything else might be a bit optimistic.
Yeah, I was assuming 4, but it could be much longer. 7 has been, happened before, that's for sure. Governor Newsom strongly supports this project. When the Biden administration announced it, he had a joint announcement with them. So he's pushing hard for this thing as well. Yeah, I think at least as of right now, that could all change with the future elections, but as of right now, there's a lot of political support behind this.
Where do you think the other 90% of the renewables are going to come from that Biden, if this is 10% of the portfolio that Biden wants to see?
Along other parts of the coast, actually, when they approved the Morro Bay project, they also approved a project up off of Humboldt, which is, I think it's more modest in size, but comparable. And I expect there's going to be, I know there's a lot more being developed along the East Coast on the continental shelf there. I haven't heard of anything in the Gulf Coast yet, but there's a lot of resource down there. So it's going to be along the entire U.S. coastline, I think.
Hey, Mike, I was going to ask, so who's behind the project? I mean, it's gotten support by Biden, but who came up with it and proposed it, put it out there?
That's a good question. I don't really know. I don't know the long history of this. I know it dates back a number of years. I think there were a couple of companies, some of which may no longer exist. I can't quite remember their names, that basically put forward proposals. I know that Congressman Panetta and Congressman Carbajal have been advocates for it, and they've tried to push it along. I'm pretty certain Vice President Harris has also been a proponent of the project. In terms of the companies, I don't know. I know there's a couple of companies up in the Bay Area that have made proposals and will probably be players in this. But it's a question of who wins the lease and who gets the permits to proceed.
Well, I think the current solar position is going to be very representative of the time of day issue we're going to have in in spades. During the daytime, we're going to have lots of energy from wind farms and from solar, and then at night, hopefully the wind farms will produce. But we're going to have to either use batteries or natural gas or something, or nuclear. Nuclear is wonderful because it can be a base load.
Yeah, I don't know if you've seen the book by Bill Gates, How to Avoid a Climate Catastrophe. I highly recommend it. It's really good. He talks a lot about nuclear in there. He's been a proponent of so-called fourth generation nuclear power plants. He's an investor in that. He says it up front. All the existing nuclear power plants out there are second and third generation plants, and in my judgment, they're a dead end. But there is the possibility of these fourth generation plants being an important part of the solution. There's about a half a dozen fourth generation designs out there that are on the drawing board. There have been a couple of small test reactors built. The Chinese have announced their intentions to build an operational fourth generation nuclear plant by the end of this decade. That would be the first if that happens. And we'll see how that works out. In my judgment, the fourth generation plants significantly mitigate the problems with the existing second and third generation plants. Don't completely eliminate them, but they do significantly mitigate them. And as a result, they may be part of the solution.
Anyone else? Well, I guess
I just put up
over to Brooks. Oh,
I just put up a link to there's the Center for Law and the Environment at UC Berkeley is a pretty active, kind of think tank, and they're doing a lunch and learn very similar to this. So I don't know if anybody's interested, but I just sent the link to it. I think it's next Wednesday at 1 o'clock. So this was very, very interesting. Thanks for
Sure.
Brooks, why don't we wind up?
Yeah, well, thank you once again, Mike. I always come away with my head spinning with new ideas when I hear you talk, so it's great.